If you haven't done your homework, I'm a little bit sad, but it's okay. We are at the point where things are going to start just overlapping. So Lorenzo, we are at the point where we can catch up on anything that, wasn't sitting pretty. We get to go back over the stuff. So the skills that we want to make sure that we go, yep, tick a box by the end of this lesson is that, are we happy knowing when a function is increasing and decreasing? So who can answer me that? When do we know a function is increasing? And what do we mean by increasing? Oh, excellent. Right, the slope is positive. So when we have, when we have a function, I always go to the good old cubic like so. We know that in this section here, it's going to be increasing. It's positive because your tangent at any point there, right, the slope at any point will be positive. That was what it means to be increasing. We're happy with that. Obviously going down, then it's decreasing. At that point, yes, at the local maximum, the derivative will be 0, horizontal tangent, right? So we looked at this when we did the equations of tangents and normals. It's now just being interpreted in a different way, but same skills. So we're happy with that? Excellent. So the bit that we now have to sort of remember is how do we make a sign diagram? And to know that a function is increasing or decreasing, we want the sign diagram of the derivative. Yeah? So did you get to question 2 at all? It's okay if you didn't. Question 2 of exercise 15C. I'm not going to be overly phased if you didn't finish it all, because you're going to get repetition happening shortly. So if you didn't, let's just have a look. I thought we'd just have a look at K and L, and we're going to repeat this in the next exercise coming, all right? So with K, we happy? My derivative is correct. You check it, because, I could go amok at any time. You know that. Everyone happy? X cubed, 3x squared, yep. To get our sign diagram, we put any values that make the derivative. That's what, when we're reading this, I'm reading this as the derivative is equal to 0. So when is the derivative equal to 0? And if we've got any vertical asymptotes, so any place that our derivative is undefined, that's also going to go on our sign diagram. So we've got that as checkpoints. We look at this. I've done I see a common factor, pull it out. But you didn't even have to do that, because we're going to make sure we're not hurting our heads. So how do we get the values? Because I look at this and straight away I go, oh, there's no way. Factors of 1, that give me add up to be 4. No way, Jose. So use these calculators that you've paid a bit of money for. Exactly. We're going to go to polynomial, so exit. We're going to go into equation, poly, degree 2, yep. Pin your values. Now I've put in 1 minus 4, 1. Can some of you actually go, do you know what, I'm that good, I don't even need to pull out the cubic. So you can put in 3, minus 12 and 3. Will you get the same answers that I do? And I hope all of you are going, of course we will, of course we will. So we get the 2 plus root 3, 2 take root 3. So that's what goes on our sign diagram. Bit of a tip. Look what I've done on my sign diagram. So I like using exact, because that's what we want to refer to when we're going to say when is it increasing and decreasing, exact. But I clearly put what those values are, because I don't know about you, but I don't know what 2 take root 3 is exactly. Why do I need to know that? Because I now need to pick a number beyond 2 plus root 3. I'm going to be safe with 10. Where do I put that 10? Do I put it into the original function, or do I put it into my derivative? So the answer to that is, what are we actually wanting from our sign diagram? We're wanting to know when is the function increasing or decreasing, and to do that we need to know when the derivative is positive or negative. So we need to put it into your derivative. So you pick a number beyond 10, and you don't have to work it out too much, but look, you got 10 squared, well, minus 40 plus, it's still always going to be positive, isn't it? I don't care what the value is, you pop a positive in there. Pick a number between. Take your headphones out, please. Pick a number between 0.2 and 3. Yep, 1. Can't go. So this is why I put the little things here. I can't go 0. 0 would actually be on this side. No, that's perfect. That's what you want. That's why I've said put these little things here, because sometimes we automatically think, oh, 2 minus, it's going to be a negative, but it's not always. All right? So might as well do 0. No, that's going to be positive and negative in the middle. We happy? Now we haven't finished, because this is where we need to use our notation, because the question actually asked, if you've got it open, it asked when is it increasing, state the intervals for when is it increasing and when it's decreasing. Yeah? So let's make sure this is correct. So I will, very technically, I will say increasing. If you want to actually write increasing, feel free. But that's my increasing. So when can we say? Are we able to use that shorthand? Yes. Yes. When are we saying it's increasing? So that part there. So this would be when x is less than 2 take root 3. And I hope you come over to my side. And when you look at the back of the book and they say it's less than or equal to 2 take root 3, you go, no. No. Because if you do that, you will also be saying that it's greater than, so it's thinking at 2 plus root 3, but then you'll be saying it is also decreasing at 2 take root 3 and 2 plus if you're using the equals to, and I don't like it. Now, please, this is language, mathematical language, because we've got this little section here. See how it's one little gap, it's in between? This is how you must write it. We're saying x, it's less than 2 plus root 3, and it's greater than 2 take root 3. It's one section. Don't break it up into 2. Are we happy with that? So your derivative stuff, right? If everyone's done this, yes, they can simplify. Yes, they can find the derivative, right? All good there. But now, can we solve for when the derivative equals 0? So, who's going to give me a heads up? It's not up. Don't think there's a trick. Do say the obvious. You could move it to the other side, but I sort of want to try and keep it on one side. Remember we talked about that. Sometimes if you move it over, you might lose a common factor sometimes. I mean, you will probably get the same answer if you move it to the other side in this case. But what if I did this? Does that give you a little bit of a heads up? So what will you do now? Common denominator, very good. So our common denominator, we times them together. We get 1 times x squared is x squared. And then we cross multiply. So we get x squared take 2. And do you have to then go any further? You probably can already see that, you know, I mean, you can do this bit if you want, but it's difference of 2 squares. Now, I like to call them my critical values, because remember, we want when the derivative equals 0, but also any asymptotes, vertical asymptotes. When we have a fraction like so, clearly it will be 0 if the top line is 0. So what makes the top line equal to 0? Plus or minus root 2, right? And do we, I mean, I put a comma there, but do we have a vertical asymptote? Yeah, Hames, where? 0, because if x is 0, makes the denominator 0, and we don't like that. That's where it's undefined, aka, so I'm going to go vertical asymptote, x equals 0. Okay? Well done. So I was about to say, and hopefully you remember from the work we did in first semester, but if you didn't, that's okay. We put root 2 we put minus root 2, but your asymptote has to be represented with a dotted line. No, you don't have to, the label is underneath at the 0, so that's indicating it's a dotted line. I think what you're thinking about is when you graph it, you have to make sure you label x equals. That one would be hard to label because it's right over the y axis. But anyway, and now we do the same thing. We go, let's pick a number beyond root 2. Right, 10 take root 2, positive. 10 plus root 2, positive. Well, anything squared is a positive. Huzzah. A number in between 0 and root 2. Well, 1 taken is negative, positive, negative. You happy? Minus 1. Oh, what's that going to be? Minus 1 take root 2 is going to be a minus. What's negative 1 plus root 2? That will be a positive. So a negative and a positive, it's negative. So notice, what have you noticed? It's not just going plus, minus, around the asymptote. Some shonky things are happening. And then when it's negative 10 take a thing is still negative, but negative plus root 10, that is also negative. Negative times a negative is a positive. And I'm not checking the bottom because I know when I square a negative, I'm still going to get a positive. So when is it increasing? It is increasing when x is less than minus root 2 and when x is greater than root 2. And it is decreasing when x is less than 0 but greater than negative root 2, and when x is less than root 2 greater than 0. Tom, Lorenz. The tangents at points A, B and C are horizontal. And we go, yeah, fair enough. We probably knew that one. Maybe not C, but do you remember part of your investigation that you did with the polynomials? This is when we've got a bit of a kink. And yeah, these are all stationary points. So stationary point here, and stationary point there. Right? What does it look like at the kink? And I did cut and paste, I think, and pop this in OneNote, but again I go, ugh. So love this diagram. When you've got increasing, decreasing, clearly maximum. Decreasing, increasing, minimum. And then this is what I like to call the kinks. When does the kink happen? Yes, well they all are when they're 0. It's when you've got a double root in your derivative. So something like x take 4 squared in your derivative. That's when you're going to have plus plus or take on either side. And that's when we've got a kink. So you look out for it. We know it's there. That's a lovely little diagram to have on your notes. All right, here goes. So A, we're going to classify points A. I mean, you might go, are you serious? I don't want to write this down. What is A? It's a local max. And you think, really? Is that all they're asking for? Yes, that's it. You're annoying me just a tad. Right, what's B? So go back to our beautiful. It's a stationary inflection. I also refer to that as a, oh God, lost it. So yeah, it has to be a stationary. These ones, A is technically a non-stationary point of inflection. or a non-horizontal. This one is a horizontal point of inflection because if I was to draw a tangent, it actually goes whoop, a bit like that. Horizontal. Anyway, and C, no guesses, no prizes there. That is a local min. And you go, well, that hasn't strained the brain. Thank goodness. Okay, draw a sign diagram for the gradient. How are we meant to draw a sign diagram for the gradient? I don't have to find the equation. What I know is at what points on that graph, at what points is the derivative equal to 0? Time of day? B, definitely. A and C, right? All of these, aren't all of these when the derivative equals 0? You find your stationary points, local min, local max, and your stationary point of inflection. It's all occurring when your derivative is equal to 0. So that's going to be minus 2. Oh, that's very messy. Oops. Oops. Let's redo that. I'm going to draw it straight under the graph, just so you can sort of suss it. So that's at 0. This is at 3. And then we've got minus 2. A sign diagram wouldn't be complete without signs. Bless you. So it's the finger, not the rude one, but your pointy finger. We're moving along here. I'm moving up, positive. Oh, now I'm moving down. Oh, still down, and then up. It's that simple. Just done the whole, when is it increasing, decreasing? So I'm assuming you can tell me. Increasing, less than minus 2, greater than 3, in between 3 and minus, like, they will probably say between 3 and minus 2. I would put a little comma, not at 0. X does not equal 0. Because at 0, it's actually 0, which is not increasing or decreasing. All right, draw a sign diagram, for f of x. And you're going, didn't we just draw a sign diagram? But what was this sign diagram for? It was for the derivative, the gradient. I like that terminology. So maybe we should get used to even labeling so we know and we don't get mixed up. So that was our sign diagram for the deriv. Let's have a look at the sign diagram for our actual function. Oh, wonky line. So do we remember what the sign diagram is for the function? The roots, because we're looking at when is the graph above the x-axis, that's when it will be positive, and when is it below, that's when it will be negative. So what's going to go on my negative 4? Zero again. And 5. And after 5, positive. Between 0 and 5, it's below the graph, so negative. So it's really important that you know what these sign diagrams represent. And that's between b and minus 4, it's above, and then it's below. And then year 12s will also have to draw a derivative for their second, sign diagram for their second derivative, but we don't know that just yet. Then you shouldn't be talking. All right, so we're going to go, we don't even really have to write that down. Classify P and Q, local max, local min, and B. All right, if we had questions like this, we'd do it all day, every day, no fractions or anything. So we've got 3x squared. 12x minus 15. I can't help myself. I like to pull out the common factor. But if you don't want to, you do not have to, because you could go straight to your calculator here. Again, I can go, ooh, this will factorise to be x plus 5. X take 1, but by all means, check. Right? Just had my year 10s do a skills test on factorising. They were allowed a calculator and they still didn't factorise things. Yeah, I know. You were like that though, I'm sure, in year 10. I'm sure you were like that at the start of the year as well. Oh, so that's B. I'm now rolling into C over here because it says find the coordinates of P and Q. Right, so because they're a stationary point, I have to find. So I already know that for P is going to be minus 5. How do I find the Y value? Put the X value into that one. Yeah? Because, why is it negative 5? Because I've factorised the derivative. I'm solving for when it equals 0. Now, I just can't be stuffed opening my calculator. Whoops. But you could just pop this into your calc. Exit 3. Was it negative 12? Normal 12. 12, negative 15. Yep. But I'd like to think if it's factorisable, you'd notice and you didn't even have to go to your calculator, but always, I guess, double check. Yes?
What did you do between the second and the third step?
Second and the third?
Yeah.
So this is factorising. So we've gone, what two numbers times together give you 5 minus thereof, but adds together give you 4. So you don't like factorising, so you pop it into your calculator and you'll get these. Now, another thing, start working smarter, possibly not harder. Because I now also have to go, Q is 1 something, and I have to sub that back into the equation, you've got 2 options. You could actually graph this. You've got it, and then go Y calc when X is minus 5, when X is 1, and you get it. Or you can use your normal run mode, pop that in, and you don't have to keep typing. You can replace X with minus 1 and minus 5, minus 5 and 1. So up to you. So I'm going to leave you. I think you could do that, your good self. The substitution. So define the points, absolutely you could have to do it by algebra means. If it says algebraically, then you probably would. Although sometimes it's like find the derivative, do all that stuff, and they don't mind if you use your calculator there. But yeah, I'd like to think at this point in time you can factorise. So get cracking with 3. Everything should be pretty good to draw a sign diagram, right? Intervals, increasing, decreasing, we've got this. Find and classify stationary points, agreed. Maybe you might forget about what we did with D, but it's not that bad. But I'd say straight away, go to your calculator and graph this, and then you're just describing. So give it a go, pause the video, and then you can have a look in a minute. So if we're looking at this, the only critical values are going to be when X equals 3 and X equals minus 3. There's no asymptote. There's no fraction, there's no square root, there's nothing. So these are the only critical values that I have. All right, so to find when they are increasing, decreasing, I need a sign diagram. So we go to B and we pop in minus 3 and 3, and we pick a number beyond 3, so 10. 10 take 3 is positive, 10 plus 3 is positive, bang. Pick a number in between minus 3 and 3. That would be 0. Okay, 0 take 3 is negative. 0 plus 3 is positive. What's a negative times a positive? Right, pick a number beyond minus 3. Minus 10. Minus 10, take 3 is a minus. Minus 10 plus 3 is also a minus. Minus times a minus is a plus. If you want to actually put it in your calculator and go 10 take 3 times 10 plus 3, you can do it. But I don't care about the value. I just want the sign. And now, so when is it increasing and decreasing? So it's increasing when x is less than minus 3 and when x is greater than. It is decreasing in between, right? Why is this 2 separate and this is 1? Because here, separate, separate. Here, 1, it's in that gap there, 1 section. I'll finish the rest so you can listen to it on the video if you want. Okay, so we've done the increasing and decreasing part there. Now the next bit is to find and classify the stationary points. So hopefully what we know by that is it a maximum, a minimum, or a point of inflection. Okay, so if we look here at the 3, minus 3, it's increasing and then decreasing. So at minus 3, we know we have a local max. And of course it works the other way, that if it's decreasing and then increasing, here we've got a local min. So how are we going to find out what they are? So we'll say it's our local max. Oops, that's meant to be an x. Minus 3, that's our x value. How do we find our y value? Well, again, what's the thing that says y equals? It's this thing here. So we have to pop minus 3 back into that. So let's grab our calculators. Menu 1, we will say 1/3 minus 3 cubed, take 9. So take 9 times negative 3 plus 4. Oh, maths type, don't you just love it? Oops. Well, you get the gist, no, better do it. You were probably yelling at me on the video, weren't you? Going, you've got maths type on. Oops, so 22. Okay, so minus 3, 22. And then, of course, you'll do the same for the local max. Describe the behaviour. So some people were talking about what's going on with this. Look, the easiest way to do it, I mean, you could just plug really large values in place of x. So put 100, put 1,000 and see what happens. But an easier way is just to look at the graph. So we've got 1/3, let's see if I can remember, and I can't already, cubed, what was it? Minus 9x, take 4, plus 4, knew that. Okay, we don't want to draw that one. There she blows. Okay, you could zoom out if you wanted to. Yep, zoom out. So what's happening? As x is getting bigger and bigger and bigger out here, right, your y value is getting larger. So we will say that in mathematics. So what's that? Is it d? D. So as x is approaching infinity, the y values were getting bigger and bigger. Remember, f of x is just fancy pants for y, so that is also tending towards infinity. And as x is getting bigger and bigger this way, your y value is also going more negative. So same sort of thing, x is tending to negative infinity as f of x is also tending to negative infinity, getting bigger and bigger and bigger. Okay, and then sketch your graph nicely. Look in your textbook to see what's going on there. So hopefully you don't have to finish, what was it, the 15C maybe, you're just carrying on. Or maybe this was 15C. Maybe you didn't have to finish 15B. So don't have to finish 15C, just make sure that you do as much as you can of 15D, go back, check the OneNote for first principles. So just try and make up as much time as you can. Cheers.